So hello, everyone. Today, Austin, Adam, and I will be presenting a comprehensive survey of machine learning and AI attacks. Due to time constraints, we will each only cover a high-level explanation of our individual topics. For more details, you can reach out to us and we can send you our paper. So a little background, AI tools are becoming more integrated into our daily routines. There's a persuasive reliance on these systems, which emphasize the need to promote awareness of potential threats. And the public is already viewing a lot of these models as truth, which gives incentive for attackers to exploit them with malicious intent. And so one of the issues right now is currently there's an underwhelming awareness of security threats amongst machine learning and AI professions, as well as a lack of standardized metrics to identify these attacks. So this hinders the effective identification and mitigation of these AI threats. So our work explores machine learning attacks, and we categorize these as AI poisoning, inference, and evasion attacks, and we'll explore their implications and current defense strategies to promote awareness. So now the first one is AI poisoning, and this is an attack where the adversary has a way to manipulate the training data directly of an AI system. And there's four main types of these attacks. There's backdoor attacks, and in these ones, the attacker will insert a backdoor signal into the training data. And when the model sees the signal during testing, it can produce a predefined output based on the attacker's design. A simpler approach is a label flipping, where the attacker can alter the labels in the training data to cause confusion. And then more advanced techniques are the attacker can use something called feature collision or pattern injection, where the attacker can craft inputs similar to one class, but near another class's boundary to mislead models. Now, the figure here on the screen shows that most algorithms are actually susceptible to these attacks, with the exception of k-nearest neighbor. And this one's just less susceptible because it doesn't undergo a traditional training phase, but rather it memorizes the entire training set. And then the predictions are made based off the similarity of new instances to the existing data points. So there's no distinct learned decision boundary or complex parameter optimization that's susceptible to this poisoning. So in order to make this work, you would just need to poison a lot of the data initially, and that would become obvious to the initial user. Whereas you just need a few instances to affect biases and weights for like more complex models like neural networks in the random forest. Now, currently, there isn't a robust standard metric to identify poisoning. So most defenses are just using monitoring techniques and data analysis. So the offense uses monitoring techniques by looking at training data for abnormalities, unexpected patterns. They'll conduct outlier analysis and compare model behavior against benchmarks. They can also employ adversarial testing and use tools like data provenance and auditing to track the data's origins in order to keep up with data set integrity. And there are more complex methods in research. They're just currently not the standard, but they do offer defense mechanisms such as evaluation metrics exclusions or gradient analysis. And these methods, they're aiming to counteract the malicious updates by penalizing adverse impacts on whatever metrics that they're using or extracting discriminative features to detect these attacks. Now, interestingly, not all AI poisoning is actually viewed as malicious. So in the creative world, professionals in creative fields actually leverage poisoning techniques like glaze to protect their artwork from actually being exploited and used for AI-generated reproductions. And additionally, these theories propose poisoning AI models can render a lot of the software ineffective because it'll impact user satisfaction and potentially lead to the downfall of creative AI services. So now I'll go ahead and pass it on to Adam, who will talk about the next topic.
So the goal of evasion attacks are to get a model to misclassify some input data. And what makes an evasion attack different from a poisoning attack is that it takes place in the testing phase rather than the training phase. An example of an evasion attack can be seen in the image to the right, where a picture of a panda is initially classified as a panda. But when we add a small perturbation to that image, it gets classified as a gibbon. Some common evasion attacks are gradient-based attacks, where the attacker exploits a model's loss function to create input that can be misclassified. Transfer attacks, where the attacker attempts to reverse engineer a model and use that reverse engineer model to test attacks that can work on the real thing. And physical attacks, where some kind of physical alteration is made to the input, such as adding a sticker to a stop sign that's being read by a self-driving car. Next slide, please. Some common defenses against evasion attacks include adversarial training, which is essentially training the model using adversarial examples, ensemble-based approaches, which is essentially using the predictions of multiple models rather than the prediction of one when classifying data, as well as model hardening techniques such as defense distillation, which can be seen in the image to the right and can be used to harden neural networks. And now I'll pass it over to Austin for inference attacks.
All right. So AI inference attacks refer to security and privacy threats that exploit vulnerabilities in machine learning models during the inference or prediction phases. In the context of AI and machine learning, the inference phase is when a trained model makes predictions or classifications on new unseen data. Inference attacks aim to extract that sensitive information about the model, the training data, or even input data itself by analyzing the responses that the model would give. So one example of that would be model inversion. It's where an attacker attempts to reconstruct or invert the original input from the data, input data from the model's outputs. So, for example, the left image of a man's face was reconstructed by an attacker, given a name and a confidence score of a target model. Secondly, we have membership inference, where an adversary attempts to determine whether a specific data point was used in a training data set. And lastly, approximate attribute, where it is a form of inference attack focused on deducing sensitive attributes or information about individuals in a data set based on predictions the model gives. Next slide, please. In this short presentation, I was going to cover more of the state-of-the-art defense tools. There are more than just these two, but to start, I would say Blur Me. It would be an excellent example where insignificant data can be used against individuals. Um, the study was performed by Weinsberg et al. In 2012 that demonstrated that purely based on movie ratings, that they're able to predict with between 70 and 80% of accuracy the gender of each user on a platform. Um, and in order to defend against this, they were able to inject behaviors of users that were not previously there to help confuse attackers. And AttriGuard similarly was developed by Jun Yang and Neil Zhang in 2020. And it was developed to counter attribute inference attacks by injecting noise into public data. This tool uses two phases to optimize the minimum amount of obfuscation required, and whether that is blur a literal pixel within an image or inject behavior to a user similar to Blur Me. We found that in comparison to other defense tools relying on a game theoretic method, AttriGuard was proven to be the most computationally intractable. So in conclusion, we found that these attacks and this concept is highly impactful and will remain an ongoing area of study. And here are our references.
Yeah, so I guess now we'll open it up to any questions.